Hi everyone, this is Worksheet 9.1, Ideal Solution Model to a Binary Solution. And I'm just having you do this one on a blank sheet of paper. Just make sure that you put this title as well as your name on that blank sheet of paper. Now, this derivation is intended to work out some of the algebra that's on page 212 of your textbook, that is section 9.3. It presents a number of equations, and I just want to walk you through where the equations come from. Although I highly encourage you to take a stab at them yourself. So if you look at equations 9.9, 9.10, 9.11, 9.12, and 9.13, then you can give it a try algebraically and see if you can get them yourself. I think that would be highly informative and satisfying if you're able to do that. And if you can, then you can just go ahead and turn that in place of this worksheet. But if you need some help walking through the algebra of those things, then that's what this video is intended for. Now, if you want, you can attempt to do just some of those equations yourself. That's fine too. But if you need help with any of them, then just go ahead and watch this video. All right, so I'd like to begin by reminding you about Raoult's law, which applies to ideal solutions. And Raoult's law says that the vapor pressure of component A over a mixture is equal to the mole fraction of A within the liquid phase of that mixture times the vapor pressure of A if A were a pure substance. And that star, remember, means that it applies to the pure substance A. But we're considering a binary mixture, meaning that there are two components, and so I'm just going to draw a container here with a liquid phase at the bottom, and the liquid phase contains both A and B in a mixture, but then the vapor phase contains A and B as well. And the mole fractions in the liquid phase and in the vapor phase are going to be different in general because the substances have different volatilities and different vapor pressures. All right, so we can say that the total vapor pressure above the solution is equal to the vapor pressure that's caused by component A plus the vapor pressure caused by component B. And we can apply Raoult's law to both of those and say that PA is just equal to XA PA star plus XB PB star. But the mole fractions of A and B have to add up to 1, so we can just say that the mole fraction of B is equal to 1 minus the mole fraction of A. And then we can plug that into that spot right there. So what we get is that P total is equal to XA PA star plus 1 minus XA PB star. And then I'm going to distribute that PB, and I get XA PA star plus PB star minus XA PB star. Now I'm going to group together the expressions that have X, and I can say that this equals XA times PA star minus PB star plus PB star. Okay, then that's actually a significant result right there, and we're going to come back to it. This is one of those equations that is there in your book that's going to come in handy, especially when we start making phase diagrams of mixtures. All right. Next, I want to get the mole fraction in the liquid phase in terms of all of my pure partial pressures and my total pressure. To do that, I'm going to subtract PB from both sides, and I'm going to get P total, minus PB star, forgot my stars up here too, is equal to mole fraction A, PA star minus PB star. And then I can just divide both sides by this expression here, and in the end I get the mole fraction of A depends on the total pressure of the system minus the pure vapor pressure of B over the pure vapor pressure of A minus the pure vapor pressure of B. And that's another useful equation that's going to come in handy for your homework. All right, now what about the vapor phase up above the liquid phase? Because we have all the equations that we need to know about the liquid phase now, but for the vapor phase, we don't know anything yet. It's going to have a different mole fraction than the liquid phase, and instead of using X, I'm going to call it Y. All right, so it can be a little bit confusing that I've got X as a mole fraction and Y as a different mole fraction of a different phase. So a trick you might use to keep them straight is by thinking of the word vapor. All right, so the Y in vapor applies to the vapor phase, but the X applies to the liquid phase. I don't know, maybe you can think of a better way to to remember them. But the mole fraction in the vapor phase is going to be equal to the partial pressure of A over the total pressure. And notice that this one is without the star, and that implies that we're talking about the vapor pressure in the mixture here. We're not talking about the pure vapor pressure. All right, we're going to use Raoult's law here for the numerator, XA PA star, and then we're going to use the expression for P total that we have right up there just a little bit higher. That's going to be equal to XA PA star minus PB star plus PB star. Great. Now I can take this expression and multiply it times 1 over XA divided by 1 over XA. And this is allowed because this expression here is just equivalent to 1. And that's going to equal, and by multiplying by 1, I get the exact same thing. But the effect this is going to have is it's going to cancel out the XAs here and here, but it is going to put divided by an XA right down there. So let me write out what this equals at the end. This equals PA star divided by PA star minus PB star plus PB star over XA. Great. So now we have the way that XA and YA relate to each other. And I'm going to put this expression for XA into this spot right here. And so that's going to make a pretty complicated expression, but here we go. This equals PA star divided by PA star minus PB star minus PB star. And then keep in mind that this is 1 over XA, so I'm going to use the reciprocal of this expression here. So the PA star minus PB star over P total minus PB star. Okay, so now we've got the unenviable task of cleaning this whole thing up. And I think that the best way to clean this up would be to multiply this times P total minus PB star divided by P total minus PB star. And again, this is allowed because this is equivalent to just multiplying times 1, and that's going to have the effect of canceling out this awkward fraction right there. And what we get after we do that is we get PA star times P total minus PB star over PA star minus PB star times P total minus PB star plus PB star times PA star minus PB star. All right, so now we don't have any more really awkward fractions within fractions. But now we're just going to focus on the denominator of that last expression up there. And the denominator is equal to PA star minus PB star times P total minus PB star plus PB star PA star minus PB star. And we're going to use the FOIL method for this part right here. So let's go ahead and do that now. We get PA times P total, forgot my star, minus the outer, which is PA star PB star, minus PB star P total, plus PB star squared. Plus, and then I'm going to distribute this one to each of the variables in there, PB PA star, that's minus PB star squared. All right, immediately we can start canceling things out. All right, so those things go away, and all that we're left is just a couple of expressions right there. It's just this one and this one. So let's put together our final expression here. YA is equal to PA star P total minus PB star. And then let's plug in our denominator. We get, I'm going to undistribute out a P total, and I get PA star minus PB star. Okay, this is another of those equations that's going to come in really handy for your homework, and now you know where it comes from. Okay, now the final thing we need to get is the total pressure as a function of the mole fraction in the vapor phase, Y. So I'm going to distribute out that variable there, and then I'm also going to separate out this subtraction here. And so this whole thing is going to equal PA star times P total divided by P total PA star minus PB star minus PA star times PB star divided by the same thing, P total PA star minus PB star. First thing we can do is cancel out those P totals, so that'll be good, and we're left with YA equals PA star divided by PA star minus PB star. And then this is subtracted from PA star PB star divided by P total PA star minus PB star. Okay, next I'm going to subtract this expression from both sides of the equation, and I get YA minus PA star over PA star minus PB star equals negative PA star PB star P total PA star minus PB star. All right, the next step is to multiply both sides by P total. And what do we get when we do that? We get P total times YA minus PA star, PA star minus PB star. And this expression is equivalent to the next one. It's a little bit of a jump, so if you needed to verify it, you could always just try it backwards and see if you get back the same expression, times P total YA PA star minus PB star minus PA star. And this whole thing just equals the expression we had before. PA star, PB star. This is negative here. PA star minus PB star. And what's cool about this is this and this cancel each other out, and we're left with just everything there that's left over, which is P total times YA PA star minus PB star minus PA star equals negative PA star PB star. Cool, then we're going to divide both sides by this, and we'll get P total equals negative PA star PB star, and this is divided by negative PA star minus PA star minus PB star YA. All right, hang in there, we're almost done. We can get rid of those negative signs, and we can distribute this negative sign to both variables, and what we get in the end is PA star PB star divided by PA star plus PB star minus PA star times YA. Oh boy, that was a long derivation with a lot of algebra, so you may want to stop before moving on to the next section and get a drink of water or take a nap or something, get some coffee. I'm going to actually right now. Okay, I'm back. The next thing I want to show you is that a couple of these equations up here can be used to make a different type of phase diagram than you've ever seen before, unless you read the chapter, I suppose, where it's a phase diagram of the mole fraction to the pressure of the system. And this would be the total pressure, by the way. So we would call this a PX phase diagram. And using our equation up there at the top that relates P total to XA, and the function describes a straight line like so, where this pressure right here is PB star, which corresponds to just pure B, because we've got a 0 mole fraction of A, and then over there, this is just pure A, so that's PA star right there. And this describes the liquid phase mole fraction. And then we've got an entirely different phase diagram that corresponds to the vapor. And so I'm going to write vapor right here. And this time we've got XA going from 0 to 1 here, and we've still got P total on this axis. And we've still got our PB star, and we've got our PA star, only this time it's connected by a curved line instead of a straight line. And that obeys this equation that you see just right up there that relates to XA. And we could call this a PY phase diagram. And that's it. That's the worksheet. I know it was a long one, but thanks for bearing with me.